Yesterday, what went on in the course of the boot camp yesterday? Well, we started yesterday with a look at the role that the critical system heuristics can play in shaping our understanding of model boundaries. And Jeff had noted a variety of considerations that I hadn't had time to go into or the opportunity to go into the previous day. These are factors involving aspects of the stakeholder environment, issues having to do with data availability in some cases, and questions as to sort of what outputs are needed to address the stakeholders, as well as some representation from people affected by the model. So Jeff had some slides on this that we'll try to get up for sharing. But drew on his background in critical realism as a sort of foundation for modeling. Following that, we went into start work building up some initial models. And we built up models that illustrated a couple key principles yesterday, as well as some ancillary principles. The key principles, factors such as heterogeneity, factors such as introducing dynamics on the part of agents, and being able to aggregate those dynamics up to the level where we could see emergent patterns related to outcomes for the whole population that were different from those of the individuals. We saw that we could use state charts to represent an individual's progression, and we could do so in a way that was scalable for different concerns associated with an individual, in contrast to aggregate modeling, where we have to deal with all possible combinations of sort of concerns at a given time, a person's characteristics, their state with respect to one comorbidity with respect to another comorbidity. When we're trying to build an aggregate model, we have to stratify it by each and every one of those in turns, and it leads to a model that blows up as you add concerns, as you add heterogeneity. With these sort of individual-based models, we're not bedeviled by those issues. Rather, we can deal with concerns in a fairly modular way. So we saw yesterday that as we built up our model, we could add, for example, state charts associated with diabetes on the one hand and with weight on another, and it kind of parsed out different sets of concerns into different pieces of the model. We saw that these state charts are useful for characterizing not just the states in which someone could be, but also for characterizing the evolution between those states. And while we didn't go into it in all the detail I would with a full 5 or 6 day boot camp, we did note that there are a variety of different types of logic that can govern these transitions. The transitions that we've dealt with thus far have been transitions that have been purely rate-based. But we're going to have a quick interlude this morning where I'm going to show you a different type of transition, a transition based on timeouts. And we'll see how it affects the dynamic of this model. We further are going to see in some of the examples that may be introduced, probably today, certainly by tomorrow, additional types of transitions as well, factors such as, or transitions such as message-based transitions, where you send an agent a message, and often that message comes from other agents, sometimes from intervention processes, and that yields an individual, say, who has been overweight to lose weight. Maybe it represents participation, successful participation in a weight loss program, and it would move them down to a normal weight state. So we have this capacity to represent not just these hazard rate-based transitions, but we also have the opportunity to represent these message transitions. We'll see again later today, maybe otherwise likely by tomorrow. We can also have an agent transition in their state chart when they arrive at a destination. So we're going to see that models like this can include moving agents that move from one place to the other. I'm hoping to look at that today for some aspects of mobility among nutritional options. So a person moving, say, to a grocery store, to a convenience store, and back, or a person moving to a place of service delivery, such as a provider's office, a doctor's office. But we'll also see that this agent arrival can also be exploited in a GIS context, either late today or more likely first thing tomorrow morning. So Dylan will be showing an example which includes GIS functionality, where the agents are associated with latitudes and longitudes, and they move in a geographic space to geographically situated resources. And it's a very powerful combination between agent-based modeling on the one hand and GIS data, so we can understand something about the exposures of agents over time to certain resources, their proximity to certain influences, etc. So we're going to be seeing that tomorrow, but thus far we've explored state charts at a fairly high level, but a powerful level in terms of representing multiple types of conditions. Now, I'd like to get you involved in some of this conversation. These two state charts that we had, were they fragmented solitudes? Did they exist totally in isolation? No. So where was the linkage between them? How was that? What sort of, on a functional level, putting aside the plumbing of how we accomplished it for a moment, at a functional level, how was this one related to this one? What was the nature of the influence? Causal. It was a causal influence. Good. And this ended up influencing what over here? Influencing, the behavior over here. Sometimes you think of it, I mean, it's a little bit of an old and sometimes rotten chestnut, but you think of the states here as being the nouns and the transitions as being the verbs. This is where the action is. This is where the things happen at the transitions, and the states represent the current status of the situation. So I am overweight, I am obese. That's adjectival. But the actions occurring at these transitions. And so typically when we talk about influence from one thing to another, we're talking about influence that changes behavior. And here it was developing diabetes. And that was dependent at a causal level of state in which you were located. Now, how was that at a plumbing level? Much of our session yesterday was probably spent in this awkward movement between two spheres. On the one hand, high-level conceptual sphere, where we were talking about grand concepts relevant to dynamic modeling. On the other hand, talking about the plumbing. How do you actually accomplish this in a model using this particular framework? And in this particular framework, how did we accomplish the linkage, the influence that being in a certain state over on the left, on the weight state chart, had on this state chart on the right? How was that accomplished? It was accomplished through what mechanism? It was a variable. So we had introduced this element of plumbing that was this variable that ended up impacting this here. And initially it was a single variable that dictated this diabetes hazard, but eventually it became two influences. One influence was through this cumulative obesity years, and another was through the current state that they were in. So if we go down and we click on, for example, this state, we find we use this so-called entry action here to capture things. And there was some developing diabetes hazard from the current weight that was captured on a per state basis. And then for this final state, we had something more involved. And at a functional level, what was more involved in this final state? What entered the picture that didn't apply for any of the other states. How was this final state different from all other states in this state chart? There was something we did for this. We accumulated the number of years. And it's handy when dealing with models and with software and all to kind of step back from plumbing and just ask at a functional level what was being accomplished. What was being accomplished is we put in place mechanisms that allow us to find the number of cumulative obesity years that people had lived. So in other words, there was a way of, for a given individual, getting back a number that reflected how long in years that individual had spent in this obese state. Do you remember that? And that happened to be accomplished through some mechanisms of beauty that brought tears to my eyes. But that's a little bit beside the point. That's kind of the plumbing of it. What's really important is the functional description, that we kept track of the number of cumulative obesity years. And that ended up also serving as an independent risk factor over here to the right, in terms of risk of developing diabetes. So we saw that we could do things like that. Now, that's quite powerful. If you consider system dynamics models at an aggregate level, there's no shortage of system dynamic models where you'll keep track of someone's current weight status. It's a beautiful and elegant model. But let's reflect on this for just a bit, if we could. How many people in here have used aggregate modeling before? Aggregate sort of system dynamics modeling? Yeah. Okay, so it's good. And I'll tell you that Jeff and I here, when we start examining a problem, we'll often start aggregate to start thinking about it. We can sketch things out really quickly and develop some intuitions. But at a certain level, there's certain effects that it's very hard to capture using an aggregate model. Just to rattle them off: aspects of spatial context, of network context, aspects of individual history, aspects of individual preferences, and heterogeneity. These are all things that are hard to kind of do justice to within an aggregate framework. And if we had an aggregate framework, here we'd be counting the number of individuals, say, who are normal weight, who are obese, who are overweight. And we might have a diagram of stocks and flows that looks very similar to this here, right? Looks very similar. It's isomorphic. It's a one-to-one mapping between what's shown here on the left and that. It would become much more ugly once we start to consider diabetes as well. But we won't go there quite yet. But the key thing is, in an aggregate model, you're keeping track of the number of people who are in each of these stocks, in each of these categories. So, maybe there's 50,000 people here. There's maybe 30,000 people here, and maybe there's 10,000 people down here. What a model like this gives you over time, a very powerful cross-sectional view of how this population evolves. But what it doesn't tell you is, maybe we look at this 2 years later, and we have perhaps different particulars. We have 15,000 people here. We have perhaps 32,000 people here, and we have perhaps 55,000 people here. There's been some population growth. What you can't really do in an aggregate model, amongst other things, is ask: how many of these 32,000 people are the same ones who are here in this state then? It abstracts over individual histories. It doesn't allow you to ask that, is it the same person over time? And it doesn't really provide you a way of asking about the previous history writ large of a person, how many times they've lost obesity and become obese again, for example. Whereas that can be very readily kept track of here. How many times someone has gone to cycle. And weight cycling is a known phenomenon when it comes to people's trajectories, individual trajectories. But an aggregate model doesn't provide the level of resolution to address that successfully. And similarly, this phenomenon that we did capture yesterday, cumulative obesity years, that's not something we can easily capture here. About the best we could do is we could keep track in this model of people, for example, according to, we could keep track, okay, these are folks over here who have had a certain number of cumulative obesity years. So these are people with 0 to 2 cumulative obesity years. These are people with 2 to 4 cumulative obesity years, and we'd have the same sort of movements between these states over here. These are 4 to 6. It gets really ugly. It gets explosively ugly. Keeping track of cumulative obesity years here can not only be done more elegantly, it can also be done precisely. We can keep track of the exact number of obesity years for an individual rather than just shoehorning it into broad categories, 0 to 2, 2 to 4 obesity years, 4 to 6 on the part of an individual. So this sort of individual level modeling is very powerful, and we're going to see in the future ways that we can further instrument this to keep track of things like occurrences, number of occurrences of obesity for a given individual to find out if they're undergoing weight cycling, for example. Quite readily done. We further elaborated this model by putting into place some mechanisms to allow for some of these hazards to vary by covariance or risk factors. For example, to have an overweight hazard that varied by age. And that led to an interesting discussion of the scope model, what things kind of assumed to be fixed and what things were endogenized so that they were varying in the model and ended up affecting other elements of the model. So, we can make this rate here from this hazard from normal to underweight to overweight be based on a fixed hazard irregardless of age, but that would lack plausibility because there are such big age effects. On the next level, we could make it a fixed hazard by age, but that would be failing to capture the dynamics of an individual's own environment that might predispose them to a high risk or a lower risk aspects such as their socioeconomic status, ethnic background, their familial context, etc., and any interventions to which they played a role. It would also prevent us from directly examining, just by changing assumptions about physical activity, how the burden of obesity would change. So if we wanted to capture the impact of physical activity, we could do so as a covariate in this relationship, and then see the distal impact of a change in physical activity on weight, and then in turn on diabetes status. So these models, in terms of some of the relationships by which they capture the factors, you can get either simpler but more restrictive relationships, or broader but more ending relationships in terms of their complexity. So we talked about that a bit. We further examined this impact of making these two state charts interacting through these use of variables that we've noted. And we saw how a person's appearance could also be affected by setting variables, for example, in the state chart. We could set a variable here, the image scale, and have the size of this vary accordingly. Or we could have the color of this vary accordingly according to their state. Okay? So that was some reflection on yesterday. And then in the final session, Dylan, I believe, had led you. And Jeff and I had to literally run out. I finished my unfortunately shortened morning run, which I had taken down by Queens Park over near Charing Cross, and I finished it on the way to the Sachs Institute, where we met the head of it just in time. And Dylan, meanwhile, was leading you, I think, on an exercise which exposed you to another set of constructs for these models. And what did that involve? Can anyone speak? when we came back, there were quite a few people still working on it. What did that involve, that exercise? Good. And at a broad level, they were connected via networks. And one agent could influence another through what mechanism? Through a message. Okay, so a message was a mechanism of sort of discrete interaction. I'm affecting you in some sort of event type of way, some sort of influence that we can reasonably approximate as kind of a short-term influence. Maybe I have an agonistic encounter with you, or maybe I impart to you some meme in a quick interaction. Messages are very useful for capturing those factors. As in the first GDM example, as we may see today, there's other types of interaction between agents that's more persistent. Think about the influence of a mother on her child's nutritional norms, something along those lines. That's a more gradual interaction. And one would model it as perhaps a series of events, particular meals taken together. Often we'd instead represent as a network between them, which led to more gradual influence, as captured perhaps, for example, by a system dynamics stock and flow connection. Networks are powerful, networks to connect agents. That particular example is drawn from communicable disease, but similar issues come into play when you're dealing with obesity, or more broadly, when you're dealing with behavioral risks, health behaviors, right? There's norms that are transmitted by our proximity to others. There are knowledge, attitudes, beliefs which travel over networks, which shape our health behaviors. Do they not? So they take our likelihood of uptaking smoking, or our likelihood of engaging in physical activity, or making an effort to eat healthy foods, or engage using a standing desk rather than a sitting desk if many other people in our office are using a standing desk. These things influence us. Winston Churchill said about our networks, or he didn't say our networks, he said about our buildings, right? We build our buildings and then our buildings build us. And so it is with networks. One thing, I'll be with you just a sec. One thing we didn't look at in that example was dynamic networks. And AnyLogic has rich support for dynamic networks, breaking and forming of new connections, aspects of networks that are of key importance in certain realms in the communicable disease space, notably for STIs. The work of Martina Morris and Kretschmer has long ago, a decade and a half ago, I think, demonstrated the very salient impacts that concurrency and shifting connections can have on a transmission level. But it's arguably just as important in the chronic disease space, in the space of other behavioral risk factors. Think about getting a person to quit smoking. Now you're dealing with a situation where, in many ways, they have a big challenge ahead of them because smoking is a social activity. And sometimes changing your behavior on the smoking front means also building up connections with others who are non-smokers and perhaps less close connections with those who are smokers. It may mean forming new friends. Those of you who work in the addictions area will know that sometimes when people struggle with addictions, there's an important step of thinking about choosing your company carefully so that you'll be less likely to be pulled back into engaging in adverse behavior related to the addiction. So this making and breaking of connections is a very real consideration when we're thinking about achieving a behavior change related to improving health behaviors related to individuals. And AnyLogic can support that very, very readily. And if there's a real interest in that, I could show some aspects of that. But yes.
Well, it would probably just lead on to what you're talking about. I mean, I can understand it like that. When you see infectious disease,
Yeah.
between infecting others based on property.
Right.
But when it comes down to social networks, and when it comes down to smokers living in
Yeah.
be able to show those associations. So
Yeah.
if you concrete examples of
Yeah.
what you can do to help how you can change those behaviours,
Yep.
outside the context of an intervention,
Yeah.
by showing those social networks,
Yeah.
then that would be helpful.
Yeah.
So I don't know where the data source starts.
Yeah. 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 There's some. Fortunately, we're entering an era where for many years, what was collected by traditional survey instruments was focused around, non-relational data. It was focused around aspects of an individual, so self-report related to health behaviors, perhaps, but eliciting relational attributes of a person, their relations with others, was not a central piece of it. And fortunately, in recent years, certainly in the North American context, there's been a very big emphasis on, for certain data sets, for example, those related to adolescent behavior, expanding them to include aspects of relational connections between the individuals. And there's some wonderful studies which have now been collected and brought to the table outside the communicable disease area, which do document fairly well larger scale social networks for certain groups, and that does involve a significant data collection effort, but it's been extensively studied, and for good reason, because we know so much of adolescent behavior takes place in a social context, in a social milieu. I could send you references to some larger data sets there that people exploited, either in terms of social network analysis or in terms of agent-based modeling, for insights related to this. There's also been an explosion of this data collection related to communicable disease. I'm not talking about, for example, some of the work with the Colorado Springs study for HIV, where they sort of really thoroughly map out networks, mapping out sexual connections in high schools, et cetera, to understand the STIs. And while I know that's not the focus of this discussion, it does shed light on aspects of network structure. Now, we additionally, my group, in substantial part to inform these models, is also at the cutting edge of data collection related to network structure. And I think I'm going to, by acclamation, based on people's hands just 2 days ago, I'm going to give a lecture where I talk a little bit about big trends I see in system science. And one of the biggest ones, and probably the one about which I'm most excited, is this growing confluence on the one hand of data science, and on the other hand, and big data, and the other hand of dynamic modeling. And there we are seeing a remarkable level of growth in our ability to collect network data in situ in a minimally burdensome fashion. And this is where it really departs from some of these traditional but newer data, these newer data sets that are focused on adolescent health, et cetera, where they were eliciting through questioning people's companionship and best friend status, et cetera. Information that was collected in previous times, incidentally, as part of like the Framingham study, but it was just used for administrative purposes, right? So if they couldn't follow up with a person, if they couldn't get in touch, they had elicited the names of 5 connections that they could contact so they could keep in touch with them. And have any of you seen the work of Christakis and Fowler? Yeah. And that work has some controversy associated with it for obesity because, among other things, some of the causal stories that they posit. But the fact is that even some of these older data sets do sometimes have a bit of network data. Anyway, these modern techniques based on mobile technologies in large part give us absolutely exquisite data. And so our system, IEPI, is an app which we started working on 6 years ago now. It's our second generation app for data collection for epidemiological purposes using wireless mobile devices. It provides exquisite patterns of networks, both in their static and dynamic form. And we've used that in randomized controlled trials run in collaboration with and funded by the U.S. CDC, in looks at smoking behavior, in looks at people's physical activity patterns, and to some degree eating habits and weight trajectories. We have an absolutely massive amount of network data associated with that, which we've analyzed in a wide variety of papers, and which we've used together with simulation models in any logic, incidentally, to look at various outcomes for interventions. And if there's an interest there, I could refer you to some things in that area, but it's hard to overstate the volume and the level of detail of that data, because we're entering a new world when it comes to understanding people context in situ, in which the behavior is embedded, and a very important component of that, their social context, not just sort of their location as captured with GPS or Wi-Fi, but aspects of with whom they're currently present and how close they are to those people in a proximity sense, as measured through signal strength. And I'll see if there's interest in I'll try to touch on this more when I give this talk, and give some examples of that sort of network data, and perhaps give some examples of why that network data has been so important to us in terms of pursuing simulation modeling investigations of intervention effects. So if there's interest, yeah, I could do that. But this is one of the areas where we are no longer dealing with our parent system science. If you look back 10 years, a lot of the when I started my work in my major efforts in health, it was between 15 and 20 years ago now, a little bit over 15. And at that time, we were in a totally different era. The data sets, the openness to system science techniques, the clarity on how it fits together with other techniques. These were all issues and discussions in their infancy. Now we're entering an era where a lot of the types of data that the system science models can thrive with, they're rapidly becoming available at a rate we wouldn't have anticipated 5 years ago. And that raises big prospects for system science models, because now we're taking a lot of those models that are more finely articulated out of the realm of sometimes speculation, frankly, and into the realm of where we actually have a lot of things we can use to at least triangulate that model's assumptions, if not to really tie them down more completely. And I'm really excited by this transition. Okay, so those are some comments. Any other questions?
Very quick one on
Yeah.
that.
Yeah.
Is this all captured through people carrying mobile phones? Is that the way we work?
Yeah. Through people carrying mobile phones, but people have done extensive studies additionally deriving networks from things like social media data, right? My Facebook connections, my connections via Twitter, or looking at other space like interactions over of Snapchat or what have you, that might be indicative of social connections outside of measuring them with smartphones. There's also attempts to elicit this sort of network data through things like cell tower connections, which are more inclusive in the sense that you don't need an app on someone's smartphone. Instead, you're looking at data regarding where people are located based on their cell tower connectivity. So you get a sense of, okay, these people are in a close geographic area. And in some cases, that can allow you to kind of approximate that those people are more or less connected in the sense that they're likely within perhaps visual distance of each other, or in close enough proximity that you might say, essentially, they have a certain probability of connection there.
This is data you don't need approval from individual phones to collect it.
Well, we go through extensive consent processes. Now, before we even started in this direction, I won't go too deep into this right now, but before we went into this connection to this type of work, even with our first generation system, which was used for largely network data collection, we went to our ethics board and we said, let's talk, because we know we can collect this sort of data, but we want to understand what the proper sort of ethical boundaries are for this, and we want to understand, for what types of uses you're very comfortable with it, for what types of uses you're fairly comfortable, for what types of uses it's on the boundary, and we really need to think about risks and benefits, and for what type of uses it's off the table. And we had that mature discussion with them, and we've been following that rubric ever since. And it's been a very effective sort of relationship. And we will go through consent processes, and sometimes it's tiered consent processes where someone opts into the study, with indicating that their data can be used for these purposes, but not these other purposes, or can be released in this form, but not that form. But we all go through, de-identification procedures and this enormous attempts on the security side to make sure it stays confidential. And it is de-identified and so on. But I will tell you that for every data set we collect like this, for those same people on whom we're collecting data, probably that same data is being collected by all sorts of corporate actors out there who haven't gone through any consent process and are simply using it for commercial gain in the most crass ways. And I stand before you as a shamed computer scientist to see, what my kind has done, in these other areas of using it for all sorts of advertising and mining of information regarding to people's habits. We go through the strictest consent forms. It's a fairly laborious task to work to get all the things hammered out if we're cross-linking it, for example, with lab data, et cetera. But we believe it's very important to let people have an explicit, informed choice with clarity about whether they opt in. It also involves, a need to really take into account the fact that some of the biggest needs for data collection relate to vulnerable populations, where there's not going to be the socioeconomic means to kind of maintain, high bandwidth data connections and so on. And so, for a lot of our studies, we paid for data plans for our participants. For the low-income participants, this can be absolutely key. Make sure that the data that we're gathering from them doesn't impose financial hardship on them. And they carry phones, and they have the option of snoozing the data collection, of stopping it, and for a certain delineated period of time if they are uncomfortable about the privacy concerns. One of the insights is they tend to exercise it quite little, that snoozing option, which is interesting. But I'll see if I can touch on these things later. Okay, great. Any other questions or comments? Okay. So can we do some more exercises? What do you think? Okay, great. Dylan, have you been passing around that drive? Okay, great. Anyone else still need it? Okay.